Okay, this is problem 6, and this one's a little different from all the others because this one is asking us to use source conversions and equivalent resistances or sources in order to figure out what the Norton values for this circuit are. And that's pretty straightforward, right? So you basically take a Thevenin equivalent circuit, and you convert it to a Norton equivalent circuit, and then you go back again, right, after combining terms. So let's just scroll that down a little bit so we can see it, right? So this is the Thevenin and this is the Norton. And so the first thing we can see is we can convert R1 and VS into a Norton equivalent circuit, right? So I'm just going to erase R1 and VS, right, and draw in R1 here, right, so that's now R1, and instead of a voltage source now we have a current source, right, and let's call that I1. Now I1 is just equal to VS on R1. Okay, so then what we can do, well, we can do a couple of things. We can combine R1 and R2 into a single equivalent resistor. They're just in parallel, so we can just one on R1 plus one on R1 plus one on R2. And the other thing we can do is we can add the current sources, right? So we can combine all of those into, now let's just see if we can redraw the circuit that it'll look like. It's going to have one current source, and that current source is going to be equal to I1 plus IS, and then it's going to have a single resistor, and that single resistor is R1 in parallel with R2, and then all we've got left is R3 and R4, right, and our A and our B are here. Okay, so then what we can do is we can turn that into, we can combine this into a Thevenin equivalent circuit, so we can make that into that, and this is going to be have a voltage of I1 plus IS times R1 in parallel with R2, and then it's just going to have a series resistance which is R1 in parallel with R2. That's also going to be in series with R3, right, and we get to there and we've still got R4 on the output. Okay, so then we can combine these two series resistors, and we can convert this voltage source to a current source, right? So then we end up with a I think I've got a marker rather than a pen. Let's go here. Maybe erase that. It's a bit too thick for my purposes. Okay, we want to do that one maybe. Right, so then we can convert this Thevenin equivalent into a Norton equivalent, right, where the current source is just I1 plus IS times R1 in parallel with R2, that's the voltage, divided by the resistance, which is now R1 in parallel with R2 plus R3. Right, so V on R gives us I, and then we're left with just R1 in parallel with R2 plus R3, because they were in series in the Thevenin. And then we've got our R4 across here again, and there's our A and our B. And so here is our IN, and our RN is just equal to R4 in parallel with R1 in parallel with R2 plus R3. Okay, and so the final circuit is just a Norton equivalent circuit, which is a current source and a parallel resistor, right? So where this one comes from here and this one comes from here. And what does that look like in MATLAB? Let's have a look at it. Right, for my values, the original I1 was 8 on 16500 to do the conversion from the Thevenin equivalent to the Norton equivalent. And then the first equivalent resistance is that first resistor in parallel with the second resistor. Then adding the two current sources we got, right? Let's just go back and see that we're adding the two current sources. Right, so this is adding the two current sources, and there's our REQ1 is this piece here, and then REQ2 is just adding those two, and our voltage equivalent, VEQ1, is just that. And then our second equivalent is just adding on R3, and our equivalent current source is just VEQ on REQ2, and then finally our R Norton is that. And that is how to do that question.